Hello, I'm Ryan Colvin, and thanks for watching my presentation. Today we're going to talk about outliers. More specifically, we're going to chat about two different methods for adjusting or removing outliers from our sample. First, to talk a little bit about outliers, I want to talk about the causes for outliers. Outliers can be caused by instrumental errors. They could be um, a misreading in one of our instruments. It could be caused by human error. Maybe we're jotting information down incorrectly, or maybe we've designed an experiment that has flaws in the design. Uh, Sometimes outliers are just a part of the population. Maybe it's just natural deviation or variability within our population and should be included in our sample. Sometimes we assume a normal distribution, but in fact it's a heavy-tailed population distribution. Sometimes we think we're working within one distribution and we find out that we're actually a mixture of two distributions and our data point might look like an outlier because of the mix of two distributions. The impacts of outliers is that they skew our sampling distribution. They create that tail within our sample distribution. There's the effect of significantly increasing or decreasing our mean or standard deviation because those two types of measures aren't incredibly robust against outliers. Uh, there's also an effect of decreasing the perception of validity. When we see a measurement way out there, sometimes we wonder if there's an error with instrumentation or design. The impact of outliers is also to mask a true correlation or create a false correlation, which we'll chat a little bit more on the next slide. Here we have two graphs. The first graph is kind of an example of masking a true correlation. Without that outlier, there'd be a nice linear regression line going through those data points that would show a strong R value or a strong correlation. But because we've added this outlier, all of a sudden the R value has been impacted so that it doesn't look like a good correlation. The next example is an example of creating a false correlation where without that outlier, those data points would not look like there's a strong correlation at all. The line would probably be a lot more flat, but then we put in this outlier, then all of a sudden there's a nice R value or a correlation that's been established because that outlier is impacting the data so much that it looks like there's a good R value. So what's the big deal about removing outliers? If they're bad on the data, why not just take them out? A lot of good statisticians would say that you should always be discouraged about taking outliers out. There's typically a lot of good reasons why it would need to remain in your sample versus taking it out. The good reason for taking it out would be that you know there's error in your system, in either your instrument or your design, and you need to take the outlier out so that your sample accurately represents the population. The bad is that sometimes outliers are expected as sample sizes increase, and sometimes you're assuming a normal distribution when there's not one. So taking your outliers out may not be accurately reflecting your population. The ugly is some folks are really wanting their test hypothesis to work out, and if they just remove that outlier, then all of a sudden the correlation that they were looking for is there. But you got to be mindful that that can create false inferences, false correlations, when those outliers are especially not due to experimental errors. So there's two ways we can look at taking some outliers out. The first one I'm going to chat about is truncating or trimming. Truncating and trimming is when you reduce your sample size by removing outliers. So if we mathematically or statistically identify a couple of outliers, for instance, this data set below, 0 and 125 are considered outliers. So when we keep them in the sample, we notice that our mean is 30.6, our median is 22.5. Good thing about medians, they're pretty robust when it comes to outliers. They're not going to be impacted because you're just looking at middle sets of data. Whereas that mean will take in all accounted sample statistics. So we look at what happens when we take the 0 and the 125 out, then our mean is drastically reduced to 22.625, and of course the median stays the same. The other option is Winsorizing. Winsorizing, we keep the sample size the same, but instead of removing the outliers, we're going to do a kind of a censoring effect on them. We're going to take 0 and 125, and we're going to replace them with the next minimum and maximum value. So we replace it with 21, and we replace 125 with 24, and then we'll see that our mean has been reduced as well again in this sample, but we're keeping our sample size relatively the same. Like I said, just more of a censoring effect versus the removing effect of truncating and trimming. That was the two methods I wanted to show you today. I really appreciate your time. I'll leave you with a quote that I came up with while I was doing this presentation. If you're going to be reduced to a statistic, aspire to be an outlier, and the average will follow you. Thanks for watching, and have a great day.